Okay, first I want to thank you, Yves, for giving me the opportunity to present and to talk about functional materials. So I am coming from the Institut de Chimie de la matière, condensée de Bordeaux, which is a lab where we are dealing with functional materials from ferroelectrics to ferromagnetics to piezoelectric materials, magnetocalorics and thermoelectrics and so on. So I'm not going to talk today about, I'm not going to give you, a catalog of functional materials, but I want to focus on specific one in order to illustrate the idea and concept that we have seen yesterday on structural materials. And I would like to show you how we can translate some of these concepts and ideas to improve the property of functional materials. And to do this, I will focus on thermoelectrics. So this is why, in the first part of my talk, I will give you the background on thermoelectricity, and then I will develop three examples. One example on each ideas that we have been talking about yesterday. The first one was about combinatorial metallurgy for alloy design, and the use also of SPS. The second one was about composites materials, and the third one would be an example of the lesson that we have learned from biological materials. So how to do better with less. So for the past 40 years, thermoelectricity have provided power for space probe or planetary rovers, like Curiosity on Mars right now. And since very recently, the automotive industry is looking at a thermoelectric generator in order to convert the waste heat from the exhaust into electricity. This electricity can be used to charge the battery, reduce the load on the alternator, and as a consequence, decrease the fuel consumption and also decrease the CO2 emission. So this is why we are looking at electricity, thermoelectricity. So on the left, you have a picture of thermoelectric generators. And as you can see, thermoelectric generators doesn't have any moving parts. It is made of many legs. And on the right, you can see the principle of thermoelectric generators. You have many legs consisting of semiconductors, P-type and N-type semiconductors that are connected in series, electrically in series, and thermally in parallel. And when you applied thermal gradients, the charge carrier diffuses from the hot side to the cold side to provide the voltage from the Seebeck coefficient, and also to have a current that is driven by the heat flow. This is the conversion efficiency of thermoelectric generators. So basically, it is a ratio of the power output that is provided and divided by the heat that is absorbed at the outside. And the power output is simply the product of the resistance of the circuit to the square of the current intensity. And the heat that is absorbed at the outside is the sum of the heat that is removed due to the thermal conduction, the heat that is removed due to the Peltier effect, and the half of the Joule heat. And when we derivate this conversion efficiency to find the maximum conversion efficiency, we end up with this expression. I don't have it. Sorry. So it's not working. So we end up with this expression, and we can see that the maximum conversion efficiency of a thermoelectric generator is limited by the Carnot efficiency, and also the key parameter here is Zt, which is the performance index that measures the performance of thermoelectric materials. This performance index is a combination of three transport properties, where S is the Seebeck coefficient, sigma is the electrical conductivity, and kappa is the thermal conductivity. As you can see from this performance index, in order to increase the conversion efficiency of a thermoelectric generator, you need to have a materials that is capable of generating a voltage from the Seebeck effect, that is capable to conduct electricity, and also that is capable to maintain a thermal gradient between the hot side and the cold side. So we must stress that this is a quite unnatural combination of properties to have this. And I have to show you, of course, the materials property space for thermoelectrics. So this was done using the CES EduPack, and by guessing the value of the Seebeck coefficient because it is not into the CES EduPack. And so we have here the power factor, that is the numerator of the figure of merit, that is plotted against the denominator, that is the thermal conductivity. The big bubbles represent materials family, so from metals to polymers and ceramic and glasses. The performance index increase in the direction of the arrow. This line represents the performance index for a value of 1. And you can see that for high performance index, there is a region that is empty of any materials. So we can conclude from this chart that if we want to improve the conversion efficiency of a thermoelectric generator, we have to extend the materials universe in this region, in the green region, which we have a big gap in the materials. But of course, there is some fundamental reason why we have this gap in the materials universe. And to explain why we have these gaps, we have to get in the property. If we look at the ZT, so the performance index of these thermoelectric materials, we can see at the numerator that we have to have a high Seebeck coefficient materials and the high electrical conductivity materials. But both of these properties are anti-correlated. When you increase the Seebeck coefficient, you decrease the thermal conductivity, the electrical conductivity, and when you increase the electrical conductivity, you decrease the Seebeck coefficient. Because the Seebeck coefficient is inversely correlated to the carrier concentration, and the electrical conductivity is directly connected to the carrier concentration. So when you look at these figures, you can see that the electrical conductivity increases with the carrier concentration when going from insulators to metals. In contrast, the Seebeck coefficient decreases when going from insulator to metals. So we have to find a compromise, and the best compromise is found for a medium carrier concentration, where we find in semiconductors. So this is why the main thermoelectric materials are made of semiconductors, and on these figures you can see the family of materials that are used in the industry for cooling or for power conversion. They are all semiconductors. In addition, we have also to decrease the thermal conductivity in order to increase the performance index. And its solids, heat conduction has two origins. First, the conduction by free electrons, and also the lattice conduction by phonons. On this plot, we can see the thermal conductivity plotted against the electrical conductivity. All the metals lie on the same line because in this family of materials, the thermal conductivity is dominated by the free electrons concentration. In contrast, you can see that in semiconductors, the thermal conductivity is dominated by the lattice part, so by phonons. So in conclusion, if we want to improve the conversion efficiency of a thermoelectric generator, we have to play with semiconductors in order to decrease their thermal conductivity, their lattice thermal conductivity. And the lattice thermal conductivity is the product of the heat capacity, the speed of sound, and here the phonon lifetime. The phonon lifetime is the key parameters because we can tune the phonon lifetime by controlling both the composition and the microstructure of the materials. And what we can say is that when engineering thermoelectric materials, we have to introduce mechanisms that will scatter phonons over a large range of length scale, from the atomic one with the introduction of solute atoms into solid solution, to the nanometer one with the formation of nanoscale precipitates embedded into the matrix, to the meso or micro scale with the grain boundary scattering. So from these strategies, from this idea, I'm going to show you 4 examples of thermoelectric materials in which we have designed the microstructure at different scale. And the first one would be magnesium silicon tin alloys. So to design these alloys, we have used the combinatorial metallurgy approach using a diffusion couple. So Mg2 tin, Mg2 Si were produced by induction melting in tantalum tube. Then the ingots thus obtained were ground and densified by SPS in order to get very dense pellets of both pure phase. Then the pellets were welded by SPS in order to get the diffusion couple with a perfect interface. And the diffusion couples were then annealed at different temperature in order to develop the interdiffusion zone. And so this is what we can see on this ACM micrograph with here the 2 end members unaffected by the diffusion and in between an interdiffusion zone that is made, as you can see on this composition profile, of one single phase, which is a solid solution of silicon into Mg2SN. So we have a nice composition profile, and what we have done with this is we have mapped the thermal conductivity across this diffusion couple. And this is the thermal conductivity mapping done by thermoreflectance. And as you can see, we can understand the relationship between the composition across the solid solution and the thermal conductivity that is related to the composition. And we have done this also for Seebeck coefficient, but we were less successful since the resolution of the Seebeck measurement is less than the characteristic of the microstructure. So anyway, from this diffusion couple experiment and also from other experiments, we were able to plot the composition trajectory of these materials in a space with the power factor is plotted against the thermal conductivity. As you can see, by mixing both Mg2SN and Mg2Si in order to form a solid solution, we improve the material performance by decreasing the lattice part of the thermal conductivity. This can be correlated to mass fluctuation defect and strain scattering, as we have calculated here with a nice fit of the data. So this is a model that we have set up, but I'm not getting into the detail of this. Next, we have also considered the effect of nanoprecipitates that we can form when we increase the amount of solute behind the solubility limit as shown by the phase diagram. You can see here a TEM image in dark field where each small white dots represent a nanoprecipitate embedded into a matrix. And you can see here the microstructure trajectory of this alloy that shows that when we produce nanoparticles into the materials, we also increase the performance of the materials because we decrease the lattice thermal conductivity. We have also set up a model to explain this effect. And here we can see the scattering efficiency of the nanoparticles as a function of their size, the radius, and their volume fraction. And we can show that there is an optimum size to minimize the thermal conductivity of these materials. Also, we have played with the diffusion path and the temperature dependence of the diffusion path into the diffusion couple. When we change the temperature, you change the diffusion path, and so you change the morphology and the nature of the entire diffusion zone. For example, at high temperature, we get this. At medium temperature, we get that. And at low temperature, we get a two-phase layer. And by doing a consecutive thermal treatment on the same materials, we can obtain a graded microstructure with a different scattering center for phonons. So here we have point defect scattering center. This is a solute into solid solution. And we have a two-phase layers made of Mg2 tin and particles of silicon with different size depending on the thermal treatment that we have applied. So this is interesting to have this because we can scatter over a very large length, phonon length scale. But this is only at the interface at of the different couple, so the idea was to produce this kind of graded microstructure over everywhere in the bulk. So to do this, we have produced melt spoon ribbons. So the melt spinning is a technique to produce, to quench liquids. So it consists to melt a liquid and to drop the liquids onto a copper wheel that is rotating very quickly. And the samples that you obtain as the shape of ribbons and the cooling rate basically are of the order of 1 million of degrees per second. So on this micrograph, you can see the cross-section of ribbons. And what is interesting is that you have a big microstructure gradient. Here, this is the side that was in contact with the wheel, and here it is the free side. And you can see that on the region that was in contact with the wheel, we have a polymorphous crystallization, giving rise to a supersaturated solid solution. But away from this side, in the remaining sample, we have small Mg2Si dendrites into a Mg2 tin matrix. So we got a graded structure on these ribbons. Then next, we pile up all the ribbons and we consolidate them by SPS in order to get periodically graded heterostructure. So you can see here the different stacking of the ribbons and with the different defects that we have. Here, solid solution, so solid atom into solid solution, and here big particles of 1 micron to diffuse another length scale for phonons. And we have a period of roughly 50 nanometers between each layer. So we haven't yet measured the property of this because this is a work that is in current progress. The next example I would like to show you, it's about nanocomposites in the lead telluride and germanium telluride system. So to produce a lamellar pattern, we have used the phase transformation in the pseudo-binary system GET-PBT. As you can see, this system consists of one solid solution at high temperature and one miscibility gap at low temperature. So we have produced an alloy with the composition given by the arrow here. We have prepared the alloy at high temperature. We have quenched this alloy to get a supersaturated solid solution, and we etch the supersaturated solid solution into the miscibility gap. And you can see here that during the transformation, so the edging, we have a moving grain boundary that is converting the supersaturated solid solution into a mixture of PBT and GET layers. And we can tune very precisely the thickness of the layer depending on the temperature of the aging. And we have measured the properties, the Seebeck coefficient, the electrical conductivity, and the thermal conductivity as a function of the interlamellar spacing. What is interesting is to see that for a given interlamellar spacing, we have a reduction of the thermal conductivity and an improvement of the performance index regarding PBT and GT that are both the constituents of the composites. So this is very interesting to note this, because if we try to predict the property of a lamellar pattern regarding this property, we end up with the following theory. So in these materials, we have layers that are connected in parallel and in series. So we can bracket the property of the composites by calculating the boundaries from the parallel and series model. And when we do this, we end up with this envelope. And as you can see, a composite made of layers cannot be better than the best constituent of the composite, which is A here. This is the power factor plotted against the thermal conductivity. And here, this is the line for the performance index. And the performance index increases this way. So with the lamellar pattern, we can never get better than the best constituent of the composite. But as you can see from the experiment, we were able to get better than the best constituent. And this is because the effect of the interface that are scattered the phonons. So this was what we can learn from this experiment. So, but of course, the layer has to be very small in order to scatter efficiently the phonons. So now, the last example. So I wanted to connect what we have seen yesterday on biological materials. We learned that we should try to do at least as good as we have with a complex structure, but with less complex structure. Until now, I have shown you very complex materials with nanoparticles embedded into a matrix, with nano layers, or with graded materials, with different phases. And it is complicated to do this because it's rely on very complex thermal treatment, and it is difficult to recycle also this kind of materials. So the idea was to use a single phase and get good properties. So the idea is instead of playing with the microstructure, we should play with the anisotropy of the crystal. And I have selected one silicide, which is a manganese silicide, having a very high crystal anisotropy and a very important anisotropy of the property related to this very high anisotropy. And as you can see, we can assume that it would be much better to have a leg with a thermoelectric leg with all the crystallites oriented perpendicular, with the C-axis oriented perpendicular to the heat flow, that instead of having isotropic orientation of the crystal. So we have tried to produce such a crystal, and to do this, such a leg, sorry, and to do this, we have used mel spinning tube. And as you can see, we have produced a nicely oriented crystal with the C-axis perpendicular to the heat flow in the leg. So this is under construction, I would say, and unfortunately I cannot give you yet the property of these materials, but hopefully soon. So to conclude, I would like to show you again this property chart. and to recall that by applying some of the concept that was developed for structural materials, we were able to fill the gaps in the property space related to one of the functional material, which is the thermoelectric ones. So thank you for your attention.